very happy to have Joaquin Turiaci from UW Seattle, who will tell us about do small black holes exist.
Okay. Thank you very much for the invitation. I will be describing some work with Yimin Chen and Samir Murthy from earlier this year, some upcoming work, and also in the middle some work done with Jan and Luca that was important for what I will tell you about. Okay, so just to say a few words about motivation. So I think it's fair to say that a successful approach to studying quantum aspects of black holes has been the gravitational path integral. So one question one could ask is how this description that is based mostly on the low energy description of gravity emerged from more incomplete theories such as string theory. I think it's a fair question to ask. I'm not going to answer this question, but we will study a system where I think this could be potentially addressed. Okay, so let me introduce the systems that we will discuss. This is so-called double Kerr-Harvey states, heterotic string, and the relation to the motivation will become clear later. So we're going to consider a four-dimensional theory that comes from compactifying the heterotic string on T6, and considers particularly states where you single out one circle out of the 6 circles that you use to compactify, and you put a fundamental string with some momentum n and wind w times around that circle. From the point of view of 4 dimensions, this state will look like some massive particle in 4D. Well, we want to understand the dynamics of these particles as we turn on the string coupling and as we make gravity dynamical. So at weak string coupling, the mass of the states is obtained from a straightforward worldsheet quantization. M is the mass of the states. QR and Q left and QL are the right and left moving momentum of the string along the compact directions. So in other words, Q left and Q right are related to the momentum and the winding in some simple way. NR and NL are the excitation numbers of the right moving and left movers. This is the heterotic string, so you see that the right mover is the supersymmetric sector because it doesn't have the -1, and the left mover is the non-supersymmetric sector. And the double Kerr-Harvey states are states where we impose that the right moving excitation number is just 0. So this means that supersymmetry of the right moving sector is preserved. And from the point of view of 4 dimensions, these look like BPS particles moving in 4-dimensional space, and massive BPS particles. And the mass of these particles is related to the right moving momentum in this way. And level matching, and the fact that the mass has to be compatible between the right and left movers, relates the excitation number of the right movers to the left movers. And it tells us that our left mover has to be excited in a way that NL-1 has to be equal to the product of the momentum and the winding. Okay. So these are states that are supersymmetric with some mass related to the right moving momentum and with an excitation number which is fixed in terms of the charges. So the first question we can ask is how many of these BPS particles do we have? At weak coupling, this is easy to count. So essentially we just need to count the number of left moving excitations that we have constructed with the right value of NL. Just as at weak string coupling, the calculation reduces to 24 free bosons in the worldsheet. And instead of, this is usual in string theory, instead of counting the number of states, it's useful to define a generating function as a function of a chemical potential tau that couples to N, where N is the left moving excitation number. And this generating function is the partition function of these 24 free bosons. And so it's 1 over the Dedekind function to the power 24. And the Fourier transform will give us the degeneracies, these dns, okay? Where N is, where I call it N is the product of N and W. There was a -1 here. NL -1 is equal to NW, but I'm going to take large charge limit soon, so that -1 will be disappearing. Okay, so this degeneracy is not protected, but the Witten index of these BPS states is protected and independent of the coupling. So if we interpret this as the Witten index of this double Harvey states, then we turn on the string coupling, we turn on G Newton, which should take the same value. In particular, we will be interested, as I said, in the large charge limit, where this index will be approximated by the exponential of 4 pi square root n. So this is the usual Carly formula for these 24 free bosons. So the question we want to understand is what is the fate of these states as we turn on the string coupling. So at finite coupling, we expect that these highly excited strings will collapse and form a black hole. We would like to understand this from gravity. The question we can ask is whether we can reproduce this large degeneracy that we found at weak coupling from the gravity description. Now, this question is a little bit more subtle than in other examples like the D1D5, where this counting has been so successful, or recently also ADS5, etc. The problem is that the VPS limit of the geometry sourced by these heavy VPS particles is a black hole that has a singular horizon. And this is what's called a small black hole. It's a black hole which has an area of the horizon that is 0, and the curvatures just blow up there. Now, so this is a known problem, so why revisit it now? And the reason is that this problem of the small black hole has two contradictory resolutions. So people propose two different resolutions, and they're really incompatible with each other. So the old version of the... Yeah.
Can you remind me why people chose to call this a black hole? But what are the other definitions of black hole that is now mentioned?
No, I think they just call it black hole because it's a limit. If you take the VPS limit of the non-extremal solution, then it is a totally fine black hole. So it's called a black hole because it's a limit of a geometry that is what anyone would call black hole. So away from the VPS limit, this behaves totally fine. It's kind of smooth horizon. It has all the properties of that the black hole would have. It's just in the VPS limit it becomes singular.
Maybe the other reason is because of the novel part.
Yeah, exactly. So another reason that is part of these resolutions is that originally Sen and double curve, but Sen in the 90s and then double curve in the 2000s, to make this more precise, they proposed that when you include higher derivative corrections to the Einstein action, this horizon will become finite, of a finite area of the, which will be of the order of the string length. So that's one resolution of this singularity that you
But I think I mean, if we're talking about an object that is no bigger than a string length, then we never really. I think a black hole is fundamentally something that's defined in classical geometry.
Yeah.
And we're sort of never quite in the regime.
The string one would be classical geometry.
Yeah, it's classical, but with higher derivative corrections.
Stringy classical.
Yeah. Yeah. So it's not the Planck size, it's the string length size.
Okay.
So if this proposal was correct, then I think it would be a totally fine black hole. So yeah, so that's one proposal about the fate of this.
Well, it wouldn't have local physics.
Yeah.
Like,
no.
totally fine black, yeah, whatever.
Yeah.
I think you could reasonably still say it's not a black hole because it's not described by
By Einstein gravity.
yeah, or just any local gravitational field.
Yeah.
And the reason I'm asking the question is that these small black holes have often been used for making claims where, you know, the fact that one's choosing those two words, black hole, it's really exploited, like to kind of suggest that it's more than what it really is. This is a very interesting question, but this whole program.
Oh yeah, I'm not going in.
It's not
That's not what I said.
making states of this thing and therefore
Yeah.
black holes are not.
Yeah. We just ask I try to formulate the question as, okay, what is the geometric description of these states? I think that's a reason.
Yeah, that's
Fair
very
question to ask. According to Sen, is string size object, how you want to call it, string size solution of the equation of motion. But there was a recent proposal by Chen Matasena from 2021, I think, or 2022, that says that there is a transition very similar to the one proposed by Saskin in the correspondence principle, where before the black hole reaches the singularity, it transitions to a free gas of strings. And they argue why this is also consistent with this counting done at weak string coupling, so they can match the entropy. So we have these two pictures and they are contradictory. So we would like to use the insights in the gravitational path integral to distinguish if one of the two is correct and when and how.
Another question.
Yeah.
Now, usually they don't look contradictory because of what you just said, right? I mean, this Horowitz-Polchinski story would seem to interpolate between the two things at the bottom, but I'm probably not reading them.
But they're different. But maybe we can, I will describe this in more detail now, so maybe you can ask again. I mean, what they say is that there is as you approach extremality, it becomes small, and then at some point it transitions to the gas of strings. Here, as you approach extremality, there is no transition. You just end up with the size of the black hole stops decreasing and it just saturates to some small value.
Is there a parameter that we can dial here that's analogous to what Horowitz and Polchinski do?
Yeah, but it's the mass. So you cannot do it.
It's only this axis.
Yeah.
So that's
Yeah.
already used up.
Yeah, exactly.
But when you're doing this, you're not changing the coupling, right? Like that's the usual thing in this correspondence principle. We change the coupling and there's some transition from black hole to straight.
Well, we will see that. The string coupling does depend on the position of spacetime. You fix it at infinity, but we will see that. That will be the first part of the talk. Okay. So let me review this black hole solution. We'll continue. So the heterotic string compactified on T6 is described by n equals 4 supergravity in 4D, coupled to vector multiplex. The Bosolli content of the theory is the metric, the dilaton, the two-form B-mu, a collection of 28 Maxwell fields, and a lot of scalars that arise from the moduli of the torus. The 28 Maxwell fields have electric charges that can be arranged in this 28-dimensional vector, where in my conventions the first 22 components are the left moving momentum, and the last 6 components are the right moving momentum of the string. So these electric charges from the 4D point of view are the momentum of the string on the T6. And Sen found the most general 4-dimensional black hole with these charges, and this is not trivial because of the scalars. So this is not Einstein-Maxwell, this is Einstein-Maxwell with scalar. The scalar appear in the Maxwell action, so it's not just Russell-Norton. So let me tell you roughly how he did it. So this theory has a duality group, which is O6,22. This is the duality group of the 6-dimensional torus. And the idea is to use the dualities to map an uncharged solution to a charged one. Now, the O6,22 is not large enough to generate charged solutions, but instead, if you assume that your 4-dimensional geometry has a compact U1 isometry, which the black hole that we're interested in will be time translation, then you can imagine that you reduce your theory not to 4D but into 3D in an extra circle. And then the T-duality generalization will be, instead of 622, it will be 0723. And this duality group is large enough to produce a charged black hole from a Schwarzschild solution. So if you don't have charges, the Schwarzschild black hole will be a solution because all the subtleties are in the coupling of the scalars to the vectors. But if you apply this transformation, you can go from Schwarzschild to a generalization of the Russell-Norton black hole scalars. So this is called the solution generating technique, where you start with a simple solution and you use the dualities to generate a complicated one. So the general answer looks very complicated, but let me just, I thought at least to show you some formula. This is the case where Q left is 0, where Q n is equal to W. This is the case where the solution simplifies a bit. This is the metric, so you see it looks very similar to Russell-Norton. It has spherical symmetry. It has some redshift factors that depend on the radius, but the dependence on the radius is slightly different than Russell-Norton. And also the dilaton, well, the other scalars also have some radial dependence, but the most interesting one is the dilaton that behaves in this way. One thing we can see is that the event horizon is located at r plus equals 2m minus qr squared over m. This is where the denominator vanishes. But when we approach the BPS limit, m squared is qr squared over 2, this r plus goes to 0. So this is the small black hole limit where the size of the horizon goes to 0. Another property is that the dilaton takes its minimal value at the horizon, and this is the minimal value it takes, and you see that when you approach the BPS limit, e to the phi is also going to 0. This means that the string coupling we fix to have some value at infinity, but it will evolve with the radial distance, and at the horizon it will take a minimal value. In the VPS limit, that minimal value will be 0, so the coupling will go to 0. The Hawking temperature is the same as the one for the Schwarzschild black hole, and in particular it doesn't vanish in the VPS limit. The mass is non-zero in the VPS limit, or the extremal limit, you have some non-zero temperature. And the extremal limit with non-zero temperature sounds wrong, and that happens because the solution is singular, precisely. That you can have extremality without. Extremality is defined as R plus equal to R minus, not implying zero temperatures because of the singularity.
The way you've written it, it seems like the dilaton is forced to be 0 at infinity. I assume you've like backed it out as string coupling.
The
string coupling can then be anything, and it's just
if I would be careful about those things, the equation will be horrible, so I just simplify it as much as I could. This is the ratio between the string coupling at R and the string coupling at infinity. Okay, so this is the thermodynamic of this black hole. As the mass goes from infinity to the extremal one, the temperature decreases. So this is kind of like the Schwarzschild black hole. It has a negative heat capacity. And when we approach the VPS bound, the temperature actually remains non-zero, which is the one funny feature. And the entropy decreases as we raise the temperature, and it goes all the way to 0 at here 1 is the VPS mass, and this T is the extremal temperature. So all these ones are with respect to these natural units. So in the dashed line part of the curve, the two derivative approximation breaks down. So we don't know what happened there. Okay, so let me summarize this proposal by Chema, Dassen, and Witten. And in our paper, we did some, well, the discussion was more general, and we figured out some details related to this specific heterotic string solution. So they propose that as we approach the VPS limit, there is another contribution that takes over, this self-gravitating string of Horowitz and Kolczynski. Let me remind you how this works without charges. So if we consider string theory in the thermal ensemble and raise the temperature, when the temperature approaches the Hagedorn scale, the black hole will be a order of the string size, and they propose that there's a transition to some excited string. And one way to see the transition is from using this winding mode. So when we approach the Hagedorn temperature, there is a mode that becomes very light, which is a string that is wrapped in the thermal circle. So this is, when you take the tachyon, it has a negative mass squared, if it's, for example, for the bosonic string. If it's wrapped, the thermal circle, it will get a positive contribution from the curvature of from its wrap in the thermal circle. And the Hagedorn temperature is precisely the one where these two effects balance each other, and you end up with a very light mode. And then you have to include this light mode in your effective theory. So the equation of motion that they solve are the equation of motion that you get from compactifying to 3 dimensions of the thermal circle, involving this winding one mode, this light mode around the thermal circle, and the Newtonian potential phi, which is the length of the thermal circle. So Horowitz and Kolczynski argue that near the Hagedorn temperature, where the black hole is order of the string size, these are the two relevant fields to take into account in the analysis. So the solution looks like this. They have to find it numerically, so I will write it down. At infinity, this Newtonian potential is 0, and then the size of this thermal circle decreases, but remains always finite in the interior of the geometry. In particular, there is a region where this winding mode scalar condenses and it has a non-zero value, and that's where the thermal circle takes its minimal value, but it never contracts. And this solution doesn't have a horizon, but as emphasized by Chema, Dassen, and Witten, it has an entropy because the mass of the winding mode depends on the temperature. And then the action, even though the thermal circle doesn't contract, the action is not simply proportional to beta, it produces a classical entropy. And Horowitz and Kolczynski introduced this to show how the black hole connects to the gaseous strings. Okay, so Chema, Dassen, and Witten used the exact same solution generating technique that Sen used to find his charged black holes, but on the self-gravitating string. And they construct a self-gravitating string that has momentum unwinding on the compact space. And let me just say they compute the classical entropy of this self-gravitating string, and they get an answer that is precisely the same. This is if you write in terms of Rydell momentum, and this is right in terms of N and W. This 4 pi square root NW is the same of entropy as that one computed by the indexer. large charges. So this matches the entropy of the double Harvey states, although it's not something that you should take as being too surprising, because this is the same string that they use to compute their entropy. It's just in a slightly different regime, but it's not. This match is not surprising as other examples. Okay, so in the gravitational path integral, they propose there is a transition, not a phase transition, it's a continuous transition from a path integral with a contractible time circle describing a black hole to a path integral where the time circle stops contracting and has this topology, and instead we have this gravitating string. Okay, and the thermodynamics of the two-charge black hole, very close to extremality, is replaced by the green curve, the orange curves, which have a more standard behavior, whereas you approach extremality, the ground state of your quantum system describing the states, the temperature actually now turns around and goes to zero. And the entropy also turns around, and instead of going to zero, it goes to this S extremal that matches the double carrying entropy.
So sorry, so the S2 contracts in the string gas phase?
Yeah, it is the same topology as thermal flat space.
So there's like an end of the order from the perspective of the...
No, it's just like the origin of spherical coordinates.
Oh, sorry.
Yeah.
Can you just go back?
Yeah, it's just...
Oh, I see.
Yeah.
Sorry, it's the illusion. Okay.
Another question? Okay, so yeah, as I said, we filled some gaps in the description for the periodic string, but most of the new work is related to the what I will describe next, which is the gravitational index of the periodic string. And around the same time, there was an independent paper by Joaquin and collaborators. So what I want to do now is that in the macroscopic analysis, we compute the weighted, double and Harry compute the weighted index that can be extrapolated from string to weak to strong coupling. And so what I want to do is to compute this quantity using the gravitational path integral and see what happens. Okay. To evaluate the index, we cannot use the black hole that we studied so far because the thermal circle contracts. You cannot have fermions be periodic around the thermal circle. That's not a smooth choice of spin structures. So in the framework of the gravitational path integral, starting in HEP-QIS 5 by Murthy and collaborators, and in some papers we wrote with Luca, we figured out a way to find smooth contributions to the gravitational path integral that compute the index. And the idea, in the case of 4 dimensions, is to implement the -1 to the f as turning on some angular velocity, because spin statistics tells you that -1 to the f is e to the 2 pi I j. And then the black hole that contributes to the index is some rotating black hole, and the effect of rotation is to change the cycle that contracts at the horizon from the thermal circle to a combination of the thermal and spatial circle. That's what rotation is doing. And you can have fermions be anti-periodic around the circle that contracts, but still be periodic around the thermal circle at infinity. Okay? So it satisfies the right boundary condition and is smooth in the bulk. And the price to pay is that we need to add angular momentum, because if you turn on an angular velocity, smoothness at the horizon requires to turn on angular momentum as well. Let me quickly remind you how this works for Rice and Nordstrom. For Rice and Nordstrom, the most general rotating charge solution is Kerr-Newman. It depends on the mass and the rotation parameter A, that is J over M and Q. Let me redefine A with a factor of I, because beta omega will be imaginary. Then the condition that beta omega is 2 pi I reduces to the condition that R plus is equal to Q plus A. Okay? And then I can replace this equation for R plus in the equation for the temperature, and it tells me that beta is related to A in this way. So if I want to compute the index at some inverse temperature beta, that equation tells me what the rotation parameter is in terms of the temperature and the charge. So this solution is totally smooth, and if we compute the on-shell action, we will get pi Q squared, which is the extremal area. Even though the solution is non-extremal, it has a finite temperature, the area of the horizon is not the extremal one, but the on-shell action still is temperature independent and equal to the extremal area. Okay. The Kerr-Newman solution with this value of the angular velocity can be written in the so-called Israel-Wilson coordinates. Here you replace the usual coordinates by a spatial base parameterized by x1, x2, and x3, and the time coordinate t. Then the form of the metric is this one. It depends on the redshift factor u and a vector omega. And these are given in terms of two harmonic functions h and h tilde. Okay, if you want a solution that is HEP-QIS but not necessarily extremal, one can show that this is the most general solution you could have in the Rest-Norson case. And matching with Kerr-Newman requires these harmonic functions h and h tilde to take this simple form with these two poles that xs and xn. These are two positions that are arbitrary because you can translate the solution and still get the same solution, other than the fact that the distance is fixed by the rotation parameter A. So this representation of the solution will be useful for what I'm going to say next. Okay, but the thing that this solution doesn't manifest is the presence of the horizon. So there is singularities here. Naively, the potential singularities appear at two positions in space. But if you're more careful and solve the equation for omega, you'll see that there is a potential singularity in the whole line from xn to xs. And making the geometry smooth along that line is the same as making the geometry smooth at the horizon. That line becomes the horizon. To draw a picture, I think, well, we explained this in the paper with Luke and Jan, but I think this part, at least the discussion, was understood by Harter and Joaquin a while ago. This omega vector has a singularity in a line between these two poles, and if you map it to the standard Boyer Lindquist coordinates, this line between these two poles becomes the actual full horizon. So if you compute the area of a surface surrounding this line and you take it to zero, it's actually non-zero and equal to the horizon area. So geometrically, this representation is less transparent than the usual one, but it will be more useful to find these supersymmetric solutions. Okay. Just any question on that? Okay. So let's go back to the heterotic string. Sen contracted not only the charge solutions, but also the charge and rotating solution of this heterotic gravity theory 4D, and the approach is the same. You start with now we start with the curved black hole. That is a solution of the equations of motion because the scalars and the gauge fields are not turned on, and then you apply the solution generating technique to the curved black hole instead of the Schwarzschild black hole. Now the problem with this solution is that if you impose smoothness, saying that beta omega is 2 pi I, you end up with this equation. This little m is this is the mass of the sealed black hole, and in the BPS limit, this is related to the mass of the transformed charged black hole in this way, which is big M. And in the BPS limit, this vanishes. In the BPS limit, the little m goes to 0. Okay. So the only physical BPS solution is to take m to 0 and a fixed. And well, we wrote a paper with Ian about there are other limits one can take that still compute something like the trace of -1 to the m, but they don't preserve supersymmetry. So if you want supersymmetry to be preserved, which you want when you compute protected quantities, then this is the only combination. M to 0 and a fixed. Okay, but there are some obvious problems with this approach. So in this limit, the temperature is fixed. This is not obvious from these formulas, but it has the same problem as before. The temperature, instead of becoming a free parameter, it becomes fixed in terms of the charges. That's a problem. Now, also, since A doesn't appear in the equation for T, so T is just a function of QR, A is completely undetermined. So we have a continuous modular space of solutions that we need to integrate over. And this parameter A parameterizes the area of the horizon, which is given by little a times beta times 2. But at least for all values of A, the on-shell action vanishes and it's always 0. And this is fine because M2 derivative action cannot scale in the right way to reproduce the double Harvey action of entropy. And the first bullet point is a problem because we are supposed to be able to compute the index at any temperature. And the answer should be the same for any temperature. So this is a choice you make at the boundary of your space-time. So some condition enforcing that parameter to be fixed is very unnatural, especially for the index that should be temperature independent. So let me show you a little bit the explicit form of the solution. So this is, in general, quite complicated, the rotating charge black hole, but if you take the supersymmetric limit, it takes this Israel-Wilson form that I introduced earlier. Something nice is that this emblackening factor U that I had before, that appeared here and here, now becomes equal to the dilaton. So the dilaton takes this form. And this takes this Israel-Wilson form in the Einstein frame. And again, the rotational parameter A is the distance between these two poles of this harmonic function that appears. And in this point of view, the Einstein frame metric is totally smooth. This Israel-Wilson form is smooth. But you see that the dilaton, the exponential of the dilaton goes to 0 as you approach either of the poles. So these are the two poles of the horizon is a sphere, and xn and xs are the two poles of that sphere. And e to the phi is going to 0 at those points. And at those points, even though in this coordinate the solution is smooth at finite temperature, the solution is always, well, it would be singular if I wouldn't add rotation. When I add rotation, the solution is smooth in Einstein frame, but the dilaton blowing up in this way is enough to make the higher derivative corrections be important. So you cannot neglect the higher derivative corrections, even if only the metric part seems smooth. In other words, you can also go to string frame and then it will be singular. That's another way to say it. But, yeah. So, summarily, the unwanted features of this solution that contributes to the gravitational index. Temperature should be a tunable parameter, but we find the solution only exists for one variable temperature. The modular space is parameterized by the area, and particularly includes also the point where the area is 0. So then we go back to the same problem that we had without Turiaci rotation. And the Einstein matrix is smooth, but higher derivative corrections are nonetheless large because of this singularity of the dilaton. But since the singularity of the dilaton is such that the string coupling goes to 0 at the poles of the horizon, it's reasonable to expect that higher derivative corrections can be analyzed, because having e to the phi going to 0 means that the string coupling is small, so we don't need to include quantum gravity effects, we just need to include higher derivative effects. Okay, before incorporate, so what we will do now is to incorporate higher derivative corrections, and I will show that the on-shell action with the higher derivative correction matches the double Harvey entropy. Before I do that, I want to relate this to a description of, I want to give a universal description of small black holes in any n equals 2 supergravity theory in 4D. In particular, the quadratic string is n equals 4, so but we can do this more generally and relate to the formalism that we use in a paper with Jan and Luca on the topic. And also this formalism will be useful to incorporate higher derivative corrections, so that's also what I'm doing. So consider n equals 2 supergravity coupled to some number of vector multiplets. The two derivative action is completely determined by an object called the prepotential. It's a function of x. xi goes from 0 to nv, and xi are projective coordinates that describe the scalar fields that are inside the vector multiplets. The theory has a duality symmetry sp2 plus 2nv, which acts on this 2 plus 2nv dimensional vector made out of the scalars, and fi is the xi derivative of f. In Calabi-Yau compactifications of string theory to 4D, the leading order prepotential is given by this expression, where theCijk are geometric properties of the Calabi-Yau. So once you are given this function, at least at the two derivative level, there is a formula where you can plug it and get the action of your theory. Roughly, it would be Einstein coupled to Maxwell, but this f of x tells you how the scalars couple to the Maxwell field. Okay. So solution preserving at least 4 supercharges are generated by harmonic functions, just like in the Israel-Wilson solutions I just introduced. These harmonic functions can be written in this way. The metric takes the Israel-Wilson form. Now we have two sets of equations. first, we need an equation that tells us what the scalars are, what the profile of the scalar are in terms of the harmonic functions. So those are these so-called stabilization equations. So the imaginary part of x has to be equal to h tilde, this is some harmonic function, and the imaginary part of fi is equal to the other set of harmonic functions. And with these two equations, you can solve for the complex scalars xi. And then the redshift factor and the omega vector are given in terms of this equation. So once you are given a set of 2 plus 2 and harmonic functions, you can construct the metric, the scalar profiles, and the profile of the electromagnetic gauge fields. Well, I didn't write down the electromagnetic profile, but essentially what the equation tells you is that the residue of these poles of the harmonic functions should be interpreted as the charges, local charges of each horizon. And gamma is a 2 plus 2 MV vector that is made out of electric and magnetic charges with respect to these vector multiplets. Okay. So in the other presentation of the topic, people discuss BPX black hole solutions and restrict them to be extremal because it's the only thing that has a real Lorentzian geometry. In the model perspective, we don't care. Just you can consider BPX solutions that are non-extremal at finite temperature. They will be complex, but who cares? They give the right contribution to the index, so they should be included. But let me quickly review this whole story. So if we take an extremal BPX solution, that's equivalent to taking these harmonic functions to have a single pole, and the residue of that pole is the magnetic and electric charge of the extremal black hole. Near the extremal horizon, these scalars have a universal behavior in terms of this x star and f star. And these x star and f star are fixed scalars in terms of are fixed parameters that are fixed in terms of the charges. So this scalar moduli will be whatever you want at the boundary, but the equation that I just showed you imply that when you go close to the horizon, the scalars will flow to a value that is universally given in terms of only the charges of the black hole and independent of whatever value those scalars took at infinity. So that's given by the so-called what we call the old attractor equations. And the whole near horizon solution depends only on the charges. And this is important because the index can depend on the charges, but it shouldn't depend on this moduli represented by the value of the scalar at infinity. So the other factor was a mechanism that explains how the index could be independent of those parameters. Okay. So in the new attractor that we had a paper with Diana Luca, mentioned there, Samir, to achieve finite temperature, we need to split the pole of the extremal solution into 2 poles, and the total charge of the black hole is split in some way between these two centers in a way that they adapt to the total charge, but in principle you don't know a priori how to split them. A consequence of the smoothness of the solution, let's say if you knew how to split them, is this relation. So this comes, but let me just figure that that's just to demand that the solution is smooth at this line that connects the poles. This relates temperature. If you knew the charges, this relates the temperature to the rotation parameter A, that is the separation between these 2 poles of the horizon, at the horizon. So if you know these dipole charges gamma in and gamma s, then this is the analog of the equation in Rice-Nordstrom that tells you how A is related to beta. So what is the value of the dipole charges? Well, that's the new attractor. The upshot is that to have a horizon that is smooth and finite temperature, the value of this dipole charges is given in terms of the old attractor solution. So these are the attractor equation of the extremal solution. Now the solution is not extremal anymore, but the same parameters appear in this quantity, this gamma n and gamma s. Once you know gamma n and gamma s in terms of the charges, you go back, you plug them into the harmonic functions, and then from the harmonic function you can get the metric, gauge fields, scalars, etc. And even though the solution is not universal and everywhere in the horizon, as it was in the old attractor, the horizon is still universal at the north and south pole, and essentially the scalar becomes holomorphic or anti-holomorphic, and the non-zero value is the same as the extremal attractor value. And finally, the on-shell action of the solution depends only on the charges, is independent of the value of the scalars at infinity. Maybe to clarify, the value of the scalars at infinity is controlled by this little h, right? Because if you go to infinity, the other terms vanish. So it's independent of little h and beta, and it's this product between gamma n and gamma s, which one can show to be equal to the extremal area, independent of the temperature. So this is the point of introducing this, was to generalize the story that we have for Rice and Nordstrom to n equals 2 supergravity with vector multiplex, where there are non-trivial couplings with the scalars. Okay, so what are the small black holes in this description? The small black hole is any black hole such that the intersection product between the two dipole charges vanishes. Okay? So once you give me the charges of the, so it's something that depends only on the choice of charges. If you give me the charges, I can find the old attractor solution, and from the old attractor solution I can compute this product of dipole charges, and if this product is 0, then that's a small black hole in any theory. So for example, one consequence is that the on-shell action automatically vanishes because it's proportional to that product. Another thing we can see is that regularity that before was relating the A parameter, the separation between the poles, to the temperature, now becomes problematic, because if this parameter vanishes, then this term disappears, and now instead of being an equation that relates A to beta, this equation just tells you what beta is as a function of your boundary conditions H. So now again, we are in a situation where beta is not a tunable parameter, but it's just some fixed function of the charges, which is obviously undesirable. Another point is that another implication of this intersection product vanishing, this gamma n, gamma s vanishing, is that at the poles of the horizon, even though all the attractor values might be non-zero, the central charge vanishes. The central charge is the one that appears in n equals 2 algebra. And this is the generalization of the fact that the dilaton, if you translate it to the heterotic string, this is the analog of the dilaton blowing up at the poles. Here, vanish I mean at the poles of the horizon. So all the features we found from the same black hole are actually very universal of any black hole in n equals 2 supergravity whose charges happen to satisfy that constraint. So whatever I will say from now on will also work for any other small black hole. So before I continue, let me show you how to reproduce the result of Sen's black hole. So the compactification is done on T6, and a lot of gauge fields come from all the moduli of the T6, but the problem can become simpler if you focus on one circle, like I wrote earlier. And if you focus on one circle, you can truncate the theory to just have 2 vector multiplets, so you don't have to worry about all these 28 or 27 vector multiplets. And the two scalars that the theory with 2 vector multiplets have are determine the string coupling and moduli T that tells you roughly the size of the circle. The simple realization of the same black hole is when you take a black hole with electric and magnetic charge, where you turn on Q0 and P1. So P1 is magnetic charge for one of the vector multiplets, and Q0 is electric charge for the supergravity Maxwell vector. So if you do this, you can compare with the solution I presented earlier, that Q0 plays the role of N, the momentum of the string, P1 plays the role of the winding, and the other attractor tells you what these X star and F star are, and well, the details are not super important, but you can read off what this gamma n is and verify that the intersection product vanishes. So this is indeed a small black hole in this description as well. Any question about this? Okay, so now I will incorporate high derivative corrections and see what happens. So high derivative corrections in n equals 2 supergravity are not determined by this pre-potential f of x anymore. The action has 2 terms, it has so-called d terms. These are full superspace integrals. They are mostly unknown and very complicated. And then there are f terms. These are terms that are indeed determined by pre-potential, and in type 2 compactification they can be computed in terms of the topological string. We won't need all this, but and it's just to say that they're known. One can compute them. And to incorporate high-derivative corrections means that we should include a possible dependence of the pre-potential besides on the scalar moduli to depend on field A hat, which is a superfield whose lowest component is the Ricci square. Okay. So when your pre-potential depends on A hat, that's what tells you that when you translate it to the action, you will have integral of R square corrections to the action. It's actually also higher derivative with respect to the vector fields, but all the F terms are determined by this one function. And in this, for the application to the heterotic string, this was the two derivative action that doesn't involve A hat, and the four derivative action, the leading order correction, is this term linear in A hat, proportional to x1 over x0. And then one can have higher order corrections in A hat that will be more and more irrelevant. Oh, yeah, but for compactifications to n equals 4 supergravity, like the one relevant for the heterotic string, there are no higher order corrections in A hat. This is all you have. Something linear in A hat. And within the things that are linear in A hat, this is the leading term in the large chart.
Sorry, maybe a stupid technical question. Like, second term and the first term, do they have the same weight under the continuum transformation? I mean, the component, the scalar space?
Yeah, because A hat scales as something of weight 2.
Okay.
Yeah, so the higher the power of A hat, the X dependence should compensate. So the pre-potential has weight 2. Okay, so in an impressive series of papers, Cardoso, DeWitt, Capelli, and Mohop found all the BPS solutions with 4 supercharges in the presence of an arbitrary F terms. And we will use this. Now, you might complain that why am I able to restrict myself to only F terms since there are also other terms, the D terms? And the assumption we will make, which was checked in some cases, but as far as I know there is no general proof, is that if we focus on solutions that are, it's important, not solutions, configurations that are BPS, but not necessarily solve the question of motions, offshore solutions that are BPS, then we will assume that the D terms vanish, just by supersymmetry. And if that's true, that means that you can find the solution of the question of motion by focusing only on F terms, as long as you want to restrict to BPS configurations. I think it's quite reasonable, but unfortunately I don't know of any general proof. People check it in some case by case. Partly the problem is that the D terms are very complicated to write down, so I feel that there should be a more general proof, but unfortunately it's not.
So these F terms are just some higher expansion.
Yeah, they look, if you're applying this in the action, they look like R squared and G is related to the power of A hat that appears in the potential.
Oh, sorry.
And F are the vector
Okay. The D terms were the ones that you wrote down.
No, I wrote down the F term.
Oh, you wrote down.
D terms are not known.
I see.
They are there, but no one
I
knows
see.
them.
Okay, I got them mixed up.
Yeah.
Okay. And then this, but so what about higher powers of R?
They don't appear as F terms. There are no higher powers of R as F terms. All the higher derivative F terms involve R squared and higher powers of F.
Is that part of the reason you can solve it? Or actually, I mean, even high powers of F, like they show up all the.
Yeah, I think that would be as
So it's a non-perturbable, so it's like an all-order relation theory statement, or is it actually a convergent series? Like
I'm not getting to that, but at least in our case of n equals 4, this G comes with the power of A hat. In our case, G is 1 and there is no F.
Okay.
And in n equals 4, there is a non-renormalization theorem that tells you that there are no other terms than the one which equals 1. So then you don't have to worry about resumming. If you go to n equals 2, you can have an arbitrary set of higher derivative corrections and they're computed by the topological string. Then you can ask if those ones can, okay, maybe not.
Okay, so this is like.
This is the easiest.
Simple. Okay.
Yeah, it's the simplest case you can do where you incorporate higher derivative corrections.
And the D terms would be an infinite expansion, or they were also finite?
No, they're also infinite, and I don't think anyone knows anything about them. Almost.
But for your purposes, it's just one item.
Yeah, for my purpose, what I'm saying is that if the literals would vanish on BPS configurations
Yeah.
before you impose the equation of motion,
Yeah.
then if you care about BPS solutions, you don't need to take them into account in the variable problem. You know? And that's an assumption, but it was checked in some cases. Yeah, it appears in a lot of calculations, like in the localization, but okay, we'll comment on that later. Okay, the derivation. Let me see how much time. Okay, the derivation is extremely, and that's why I say it's an increasing series of papers. It's extremely more complicated than the two derivative counterparts, but fortunately the final answer is very, very similar. The solution is still determined by harmonic functions, but so for example, the scalars are determined by these equations in terms of harmonic functions h, but now you replace f of x by f of x and h and a hat. Before this was specified in the profile of the scalars, one manifestation that this doesn't work so nicely is that now a hat is r squared, and that can depend on the position. So essentially, this equation determines the scalars in terms of h, a tilde, and a hat. Then you go and put it in the metric, but a hat is also determined in terms of the metric. So it's an equation where everything is coupled to each other. So even though they found the solution, it's not as nice as the two derivative one, where you can explicitly write down all the parameters. So this is just to show you. So this is the equation for the redshift factor. So before you only got this term, now you have a mess. And this is the equation for this omega vector that appears in these rows. So these are no longer algebraic, and everything couples to each other.
It's not really a solution, it's the equation for e to the u, right?
Yeah. So if you give me the harmonic functions, these two equations together with this, and together with the equation for a hat, which is r squared, so it's something determined in terms of the metric, you have to solve them all together to determine both the scalars and the metric.
Mm-hmm.
Like in the two derivative level, you could first solve the scalars, and then go to the metric and find the metric.
Yeah.
Here, everything is coupled to each other. You kind of, yeah, these equations will have to be solved numerically. Okay, but in this paper with Iming and Samir, we show that even though these equations look scary and much more complicated than the two derivative counterparts, the solution is described in a very similar way compared to the new attractor that we found with Jan and Luca. Essentially, we take this harmonic function with centers that are split in two, in the north and south pole. This will be the north and south pole of the sphere that makes the horizon. And the thing we need to specify is how the total charge is split into these two centers. And the split of these two centers is again given in terms of solutions of the old attractor equations. So the old attractor equations, or the attractor equations of the extremal high derivative corrective BPS black hole, tells you that the scalars satisfy this equation, so they are exactly the same as the two derivative counterpart. But now f depends on a hat. But the nice thing is that at zero temperature, near the horizon, a hat is fixed to, in some units, minus 64. So a hat is not a free parameter anymore that you have to, that couples to other equations that need to be solved. In the extremal solution, a hat is a number. So then once you replace that number here, the equations are the same as in two derivatives. And again, the scalar become holomorphic at the north pole and anti-holomorphic at the south pole and take the value. But other than the two poles, the profile in the rest of the horizon is non-universal and depends on the boundary conditions. Okay, and another not obvious thing is that the smoothness condition that I introduced earlier takes the exact same form, this form, but the equation that determines gamma n and gamma s depend on the free potential, so that will change. The equation that determines the dipoles will be different. And of course the equation that determines the metric, which is now horrible. And finally, the last thing we need is the Hodge reaction, which we argue, we argue that it can be written like this, as a contribution of F at the North Pole and F bar at the South Pole. I can discuss that a little more if anyone is interested. I don't know if anyone is besides Luca. But okay, there are some subtleties with that, but I think the answer is correct.
So do you compute it or do you argue that this is the answer?
We compute it at low temperatures, and then we argue that it has to be temperature independent because it's the index. But there was a recent paper from CEN 2 weeks ago making some progress on this. Okay, so I will assume that this is the right action. So let me finish by revisiting the black hole solution. So this is the truncation I wrote before with 2 vectors. And what we need to do is to repeat what we did before, but add these higher derivative corrections. I put this parameter C just to keep track of what terms come from the higher derivatives, but it should be 1, just to keep track of the. The new term will produce corrections for the equations for the dipole, because as I said, this changes F, so the equations that determine the dipole will be different. And what happens is that the same choice of charges that before was given as a vanishing intersection product of gamma n and gamma s, or a vanishing extremal area, now gives us a non-vanishing extremal area that is proportional to square root of NW. That's what we had. That's already the quantity that appeared in this double Harvey entropy, and it's proportional to square root of C. So if C was 0, this would be 0. Okay. That's why I put that C there, but the end is just 1. The way you see that this is, C is 1, but the way you see that this is smaller than the 2 derivative term is that if the 2 derivative term would be non-zero, it would grow faster with the charges. That's the power with the charges is what tells you that it's a higher derivative term in my units. And that's it. So what I tried to argue before is that all the problems are rooted into this intersection product vanishes, but now that this doesn't vanish anymore, all the problems go away. Now the regularity condition doesn't fix the temperature anymore, but now it gives us a relation between the rotation parameter and the temperature that I wrote there once you replace the parameters of the double Harvey states. You see that if C goes to 0, then A goes to 0, but it's a little singular.
But is your black hole technically is not string sized anymore, or it is string sized, it's proportional to C?
No, it's not string sized because the area can be whatever you want. If the temperature is large, the area will be.
Can go to infinity then?
Yeah, it can go to infinity. So now the small black hole is a big black hole, macroscopic black hole, but with this higher derivative, classical higher derivative correction. Yeah, so the hope, so we did this calculation actually a couple of years ago. The hope will be that turning on the temperature will be enough to have a big black hole, but it happened to not be the case. Even if you turn on the temperature, you still have instead of the whole horizon being singular, just the 2 poles are singular. But the hope was that maybe the temperature would get away from all singularities. It didn't happen. We ended up having to incorporate higher derivative corrections. And I guess that's why we did this after our paper. Yeah, so now you have a big black hole that is totally smooth with this theory. And also the singularity is resolved because the string coupling is now finite at the horizon. It doesn't vanish anymore.
Okay, but just to make sure, the area doesn't have the same scaling with the charges as for the large black hole, right?
Not necessarily, no. But when you compute the action, then wait, sorry, as a large black hole.
Yeah, as a black hole for which the leading entropy does not matter.
Yeah, it grows slower than
It
sugar
grows
charges.
slower. I see. So in some sense, the black hole is still small.
It has a large area, but it has a small action. It has a small Onshel action. The black hole is large, but the Onshel action is not the area anymore. It's whatever the action is, and that is small.
That's true for any of these sort of index finite temperature calculations, right?
Yeah.
The area entropy correspondence is not true anymore.
Yeah.
Because
Yeah, I guess what slightly confuses me is that your area is still proportional to square root of C.
Yeah.
And C parameterized the correction to the prepotential, right?
Yeah.
So in what sense is the area large? I guess what you're saying is that the area of blank units can be arbitrarily large,
Yeah.
but so could the entropy of the small black hole, right? Because I can make square root of NW to be arbitrarily large.
Yeah.
Okay, maybe we can discuss more.
Yeah. Well, for example, okay, this is a kind of singular limit, but if you take beta to be close to 8 pi, you can also.
Yeah, I understand that if you take beta close to pi, you get the area is infinite.
Yeah,
But it's an infinity that still scales with square root of c.
yeah.
So that's why I was wondering if there's a different scaling even of the area itself compared to the index of the big black hole.
Yeah.
So
I
what
think what
happens if you try to take the temperature of beta less than 8 pi?
Sorry?
What happens if you go to really high temperatures and take beta less than 8 pi?
Okay, that's a good question, and that's something that also happens for the rise and north of black hole actually.
Oh, okay.
Even for the big black holes, the solution when the temperature increases too much, just has some funny behavior.
It just becomes more complex.
Yeah, essentially, for example, R plus is Q plus A in the rise and north from that I showed earlier. The solution for A, if the temperature is too large, can become negative, and then R plus can be negative.
Yeah.
So that's a complex solution because it means that if you want the solution to be smooth, you have to avoid the singularity and smoothly cap it off at some negative R plus. But if the index should be temperature independent, I think you should do that because why would the index just jump at some random charge dependent value of the temperature? Yeah, so I didn't comment on that because this is, I find it as surprising as for the big black hole. So it means.
Do you have any like that the temperature where that happens isn't significant in any way as far as we know?
No,
There's
some
no obvious physical.
4 pi over Q, well, some random value.
Yeah.
But not random. I don't have any quantum mechanical or field theory understanding of why that temperature is special. But I think the answer should be that the index should be independent and I should just take that complex solution seriously. I think that's why.
Imagine, like, I don't know, the sum stops being as nicely converted, right? Like you're summing over some things that cancel, but there's infinitely many of them, and at too high temperature, then I don't know, somehow, like
I would.
it becomes dodgier.
I would understand that if it was something conversion, but
Yeah.
tiny that can kind of blow up. But
It's
it's
not.
funnier with something that is
Yeah.
exactly zero, like the contribution of non-BPS states, it's just exactly zero. The
Yeah.
value is just.
Yeah, yeah,
I mean, one resolution is that you should include these complex geometries, and
Yeah.
that's it.
yeah.
And they violate the consistency criterion, but who knows? Maybe that's why.
But there are also, those complex solutions are around even at other temperatures. Where you can go around R plus and end up in R minus, go around, circle around
Yeah.
R0.
Yeah.
Yeah.
So I don't have an answer to all this. I don't know what I don't have a better proposal than the considered zero one, but at least in this case it looks like you should.
But what you're saying, avoid.
In this case it seems like you should, yeah. But I don't have a general thing.
Okay.
I don't think anyone has.
But I guess from a philosophical point of view, the fact that we know the value of the index tells you that you have to include.
Yeah, exactly.
So it can kind of be used to
Yeah,
set up the
some
rule.
other way, I don't know. Like,
Yeah, that's why I'm afraid that there might be some way like you're saying. I don't know how to
Yeah.
make it precise. So I didn't want to make that claim, but it could be. Yeah. So yeah, that's what we would like to do with this, right? Use the dual picture that is well understood, it's just quantum mechanics or whatever, and try to read off how we should do calculation in gravity. I think that's how we should do this program. Okay, I'm almost done. Okay, so this is obvious, but the Gaussian action of this hydrogen corrected black hole matches exactly the Harvey entropy. One comment related to what you were saying. In the new paper of Sen, so before we thought that turning on temperature we could get the right smooth solution, but in the paper of Sen we proved that it's impossible to get something that had this scaling with the charges with the two derivative action. So I think that should have been for us a hint that we shouldn't have found a smooth solution at the two derivative level, even at finite temperature. Okay, so in summary, the picture I think we should have of these fundamental periodic string states is that in the thermal ensemble it's okay to have the black hole, that as we approach the HEP-QIS limit it becomes smaller and then transitions smoothly to a class of strings. This is the Chen-Malacena-Witten proposal. I think this is the right picture for the thermal ensemble. But in the ensemble with the -1 to the f, where you compute the index, the proposal is that you just have these high derivative corrected black holes for all temperatures. So the two solutions that were proposed in the past are actually both correct, but correspond to different observables. Okay, that's the resolution that we propose. So even though the states in the thermal ensemble are string states, for the index they're still computed by a gravitational path integral that looks just like a black hole one, in terms of the topology of the solution. Even if the states in the thermal ensemble are not themselves black holes. Okay, let me skip this. Some conclusions. Well, this is what I just said. The path integral for the string index is dominated by a black hole, even though the thermal ensemble is not. I think that's funny, interesting. Another question that one can ask is there a self-gravitating string that contributes to the index? So just like there was one here, you can ask if there is another was one there. I think that would be very funny because the on-shear action has to be independent of the temperature. So if there is some transition which should lead to something that has the exact same action for some reason, I think that's kind of unlikely. But also, the winding mode that is responsible for the self-gravitating Horowitz-Polchinski solution is just not there if fermions are periodic in the thermal circle. So in the superstring, this winding mode is a tachyon that gets a positive contribution that compensates close to extremality. And the reason why you have that tachyon is that the sum over spin structures is different when fermions are antiperiodic around the thermal circle. But if fermions are periodic, then the sum over spin structures or the GSO projection works the same way as in flat space. There is no tachyon, so there is no mode that could become light in any limit. So there is no reason to expect any self-gravitating string type solution for the index. So I think that fits nicely with our picture with this high derivative corrected black hole. Another question is there is a natural worksheet description of the near pole solution. String coupling becomes small, string corrections become large. There should be some worksheet description there, but we don't know. But the gravity description seems to be simple enough that we can solve it. Another problem is to incorporate quantum corrections and maybe compare with microscopic beyond the classical analysis, maybe using localization. That's my open question. And then finally, a few other open questions. So there are toroidal compactifications toroidal compactification of the heterotic string is dual to K3 compactifications of the type 4A string, and that's fine. But what about small black holes in toroidal compactifications of type 2 string? These toroidal compactifications have no F terms at all. They are described by n equals 8 supergravity 4D. There are no F terms, but the discussion of these small black holes singularities are still there. So that's a case where we don't know how to resolve them, because these F terms are just not there. Another example that partly to me motivated, this is one of the calculations I mentioned I did a while ago. The D0 brain black hole in type 2A is dual to the BFSS model, not in the M theory limit, but in the black hole regime. The extremal limit is singular, just like the same black hole, and one can ask if turning temperature can make that smooth. And indeed, there is a finite temperature rotating black hole solution that has D0 charge and angular momentum that one would use to compute the index. But what happens now is that the string coupling blows up at the poles. Because even at extremality, the string coupling was blowing up at the horizon. That's why the low temperature has something to say about M theory. So this is a bad case, because this is also another case where we don't know what to do because it goes beyond the regime of classical gravity. So this heterotic same black hole ended up being a perfect middle ground where this can be very precise. Okay, that's it. Thank you for your attention.
Any questions for Joaquin?
Okay, maybe this is a bit technical, but in the higher derivative theory, how did you prove that gamma north and gamma south were independent of the moduli again, that it followed immediately from the equation of
we took this equation and we expanded them close to the poles.
I see it, you just found that that's true.
You just demand that there are no double poles, that there is only a single pole, and you end up with the same equations perturbatively.
I see.
So the entropy function can still be written as a product of like central charges?
The entropy function? No. In that limit.
In with higher derivative.
No, because this, whatever this is.
Yeah, but like, I mean, I can imagine that for example, the solution to this weird equation will still be like a homogeneous function and something like that.
Not in any way I can prove that I know.
I see.
I don't know how to. Yeah, even the solutions are numerical of these equations. But the analysis that we did in the previous paper was local around the poles, and that you can do perturbatively around the.
And so you're saying that around the poles, the higher derivative corrections end up not mattering?
No, they matter because they appear in F.
I see.
But what I'm saying is that in our paper we promoted the old attractor to the new attractor by a simple rule.
Yeah.
And I'm saying that the same rule applies to promote the old attractor with high derivatives to the new attractor with high derivatives.
I see.
In that sense.
I see.
But the actual solution is different because F involves a hat.
Okay.
So I guess what I'm saying is that the old attractor with high derivative corrections determines the finite temperature solution in the same way as it did for the two derivative.
I see.
Yeah, so here, near the poles, you just assume that the redshift factor goes as 1 over R and solve these equations in perturbation theory in 1 over R. And you just find that for the equations to have solution, you need to pick the dipole charge in terms of the old attractor. High derivative corrected values.
Any more questions? Okay, let's thank Joaquin again.
Yeah. Did you pick?
Do you remember?
It's not perturbative because you need to solve the equations with
It
the
had a single sign.
close to the poles it will be completely different because the
So it means it has a single sign.
what you're saying will be true if you have a solution with equations in motion and then you perturb it. But here you're not perturbing it because it's going from being singular to being so that's why this discussion about the difference is important because all the high derivative corrections will continue the same way. So neglecting high derivative corrections you're not allowed to do that. But the point is that if you impose supersymmetry then you don't have to do all for this equals 4 of application one of them. Then you can solve
I
it.
just want to make sure that there
These relations that you're looking
and I
at.
also want to make sure that
And basically, I'm not figuring out how to
So, yeah.
like dilatations.
That's true.
And like.
But okay,
and-
well, I mean, in a sense that doesn't happen in the thermal
so I guess for
the thermal ensemble in transitions so then this is not a problem. It's only off to the index.
Yeah, it makes it go. Yeah.
It's a special case, but normally you just for high derivative correction, you start at some probability solution and work out around that. So there's always two solutions, there's two solutions that come up in the
minus R.
Because in that case, that was minus
Yeah, because there is no derivative solution to the thermal. So the high derivative terms are important close to the
Where?
pole to the
Point
Here,
is,
around the
if we look at how this thing is actually
Yes, so the high thing is that this is solvable because of supersymmetry. If you didn't have supersymmetry, you have to include all the high derivative corrections.
what it is in the
Yeah,
form.
it is, yes.
Right?
And that's why people didn't took, I think some people didn't take seriously the second level proposal before, because they didn't know how to distinguish the thermal ensemble from the index. And if you tell me that this is supposed to work on the thermal ensemble, I wouldn't believe you, because why would you just restrict to this one high derivative correction without
They just meant like, include all of them, you get some stringy solution.
No, you can, that's the problem, you cannot include all of them, because you know the details.
Where this operator.
Yeah, like
Okay, I thought it was just like a qualitative proposal, like someone could figure it out.
Well, Sen has a quite clear proposal that if you include high derivative corrections, action has to have the form.
And
This
is translation here.
has to be greater.
Right, I mean,
than,
locally this is
You can show that some scale
same
but you cannot compute this number.
But you said that
The double can use this gravity technology to compute the number
The operator is the translation.
index from the string.
So
But
that
they never explain
the energy of the
very well
state.
what are the
Yeah.
what they are.
The state operator is
That's the point, that's the point. He was computing, people didn't know how to distinguish the two calculations. Now that we know how to distinguish it, you can have the correct consist continued into one, and the small black hole, let's call it correcting contributing to the other. But before all these things were mixed up.
So what do you think that would be computed? The terminal trace for like
They computed the extremity.
The classic thing between like
But that's a very singular link.
right?
Yeah.
Translations
So
of
he just ignored that and
become
computed it.
dilations. That mass
So
yes
what they're saying is that the calculation is not singular, you have on temperature, but you don't know temperature, you should decide if you're going to use approximately way or not.
thing, whatever.
Before people get
It's useful.
So the calculation was right in the ingredient size for this picture.
Y minus
The interpretation was very unclear, because if you're not telling me that you're actually computing an index,
Stay off
you don't know who is one,
This is positive.
why would
Let's
you
just so
If this
you
is
have all these other power of concept, you don't know anything. Supposedly they also think equal because you don't have this correction.
okay, and then that.
Yeah, I mean, sorry. Yeah,
So in fact,